What's up YouTube? This is Jacob from International Precision Engineering, and this is part 3 of how to software correct machine tools. So again, this is a multi-part series, and if you find yourself lost, just go back and catch up. This section here, this theory section, talks a lot about the details of what's going on behind the math and things, and sort of more of the overall concepts. And in here we'll just talk about specifically how to do it. More importantly, if you have any questions, comment. Okay, let the community throw in on this. But if you find yourself still vague or still have any questions, or if the naysayers get you on YouTube, just shoot me an email or shoot me a message on YouTube and I'll try and get to it. This part is broken up into 3 different sections. We'll talk about coordinate systems, we'll go through what actually is this kinematic chain, and then we'll talk about inverse kinematics. So the 3 of these are really more of, again, specifically how to do it, but it deals with building a model and then getting that model into sort of a software package that then you can bring your G-code from part coordinates and run it through and break that down into specifically what each axis needs to do to accomplish whatever you're trying to do. Okay, so I won't bore anybody about terminology or semantics or any rigid definition, but to me a machine tool is a machine that takes a tool and a part and does something with it. So that could be shape the part like milling, that could be measuring a part like a CMM, or that could be building a part kind of like a 3D printer, right? All of these things are machine tools, lathes, mills, everything. But fundamentally there's some kind of tool, whether it's an extruder or a touch probe for a CMM. There's some type of part that you're working on, even if the part doesn't actually exist yet, and then there's sort of machine components that coordinate the position of the tool and the part to kind of make this happen, measure, shape, whatever, right? If it's a really simple machine like this one here, we'll just say there's the tool here and it's a milling machine, and then there's a table here where the part goes, and then there's sort of one axis, right? In this sort of concept, it doesn't really matter if the tool moves relative to the part or the part moves relative to the tool, right? It's going to accomplish sort of that same task. And then the key sort of function of this machine is it's going to take a tool path, which could be the path of the part. It's just in reference to the part the tool is moving, right? So we call that a tool path. And to sort of take out all ambiguity, for example, if I say, how do I get to the mall, the shopping mall, right, from where I am? Well, you could give pretty specific directions on how to get there if you knew where you are and whatever, but the mall is kind of ambiguous, right? Am I in the left side of the mall? Am I in the right side of the mall? Am I in right first floor, second floor? So this concept of the mall, this space within this larger world that we live in, isn't good enough when you're talking precision things, right? And then also if I said I want to go exactly to this point in the mall, well, there's also ambiguity there, because am I facing right? Am I facing left? Am I looking up, down? Am I standing on my head? So this concept of this coordinate system really takes out all ambiguity. So when we say, take me to this place, what it really means, or align this point on the tool and this point on the part, again, that's kind of not good enough. We have to say, align these 2 points and then orient in this sort of way, right? And maybe some machines you don't have control of that, but in the error model it matters. And we'll see why later. So that's the advantage of a coordinate system. So what that means is we're going to pick a point on the tool, and actually it doesn't even need to be on the tool, but typically it's If it's a milling cutter, we'll say it's the axis of the cutter, and then right at the bottom we're going to call that the coordinate system. The part coordinate system, it can be whatever. It can be machine coordinates, it can be somewhere on the table. In fact, we'll talk about it later. I usually put mine 2 inches above the table because that's kind of the center of mass of most of the parts that we do. And then there's going to be a coordinate system on each machine element. And then, you know, you kind of need to keep track of all of these to sort of make this thing happen. So back to the fundamentals, how does a machine tool work? So if I come out here and close my eyes and then touch my nose, until the point where my finger touches my nose, how do I know that that happened? Or how do I know I'm even close? I'm not poking my eyes or something like that. That's this concept of this crazy word here. It just means that basically you're kind of aware of what each of your body parts are doing and then how much force you need to apply to make that happen, so you're not punching yourself in the face, you're just touching your nose. And this sort of awareness happens actually in a machine tool too, right? Like obviously you know if this is a stepper motor how many steps you need to move my axis 1 inch or 1 millimeter, whatever. But then the error component says, well, I also know that if I move 1 inch, it's going to twist a little bit, so I need to compensate with another axis to kind of bring that back. And that's this concept of proprioception, right? That's really all it means. So we're going to keep track of all these different components and what it takes to get these components to solve some particular, what we call machine pose, that serves the purpose of aligning the tool and the part with some specific orientation. And then that's kind of the gist of what's going on within your machine tool. When we talk about multiple coordinate systems, what we're really talking about is the world that we sort of surround ourselves in, but from multiple perspectives, right? So what it doesn't mean in sort of this software correction, error analysis stuff is, like, for example, in art where you say the stuff up close is bigger than the stuff farther away. That's not what we mean. And for example, in this image here, the guy on the left sees 4 beams and the guy on the right says 3, right? So no, things don't change size in various coordinate systems. They can, but not in this sort of application. So like vector graphics and things, obviously you need to take in account. But for software correction, everything is the same scale, right? And that's kind of the point. And if you look at linearity, right? So if I say I want to move 1 inch and I tell my axis to move 1 inch, but it moves 0.9999, I need to push that axis a little bit farther to get it to 1 inch. Yeah, that's a scaling issue, but that needs to be completely separate from sort of the coordinate system and things like that. And we'll talk about that again. So what I mean by perspective is, if this crazy biker guy here is on the left of the part and this Daniel Boone man is on the right, he says the part is on the right and this other guy says the part's on the left. Well, who's wrong? Or who's right? Well, they're both right. So you have to build in a mechanism to say, well, to the x-axis the part might be on the right, and to sort of the rotation axis the part is on the left, right? So we have to sort of build this concept of who's where and what's what and how everything sort of fits geometrically. And generally we do that, we say the starting point is when I hit the home button on the machine and all the axes sort of align to their homing position. That's where I want to build my model, and then we're going to start to sort of assemble these machine components into a way that we can keep track of them mathematically. Another quick note, and I said it before, but if these two situations, we'll call this one before and this one after, represent some machine pose, right? So if I call this the origin of my axis coordinate system, and then this is my part coordinate system, right? Or say this was the position of the tool and this is the position of the part. Before and after, they're in two different spots. But if I say, well, did my tool move sort of closer to the part, or did my part move closer to the tool? Does that really matter? So for example, in this illustration, it might look like the table moved, but well, how do I know that the table or the frame that, or this, what we're calling the part, is not bolted to the frame and then this whole axis moves, right? So it's sort of a gray concept of who moved where, but in the end result, does it matter, right? And the answer is no. The frame of the machine doesn't mean anything relative to where the part is and what the tool's doing to that part. So just, it helps, certainly helps to think in world coordinates, like, well, that part, you know, the 0 coordinate on the part is to the left of the, you know, x plus coordinate, but if it's a rotational machine, all of a sudden that's switched. So your concept of world coordinates needs to go out the window. Rather put yourself in the part, like glue your head to that part and say, as this thing moves around, where's the tool, right? So just keep that in mind. It's always relative from one coordinate system to another, okay? And then it could be from this one to this one, it could be from this one to this one, it doesn't matter. So because this concept of software correction is completely generic, this has got to work on every single machine that we come across, every type. This is where this concept of kinematic chain comes in. So whether it's a robot arm, whether it's a 3-axis machine like this 3D printer, or this knee mill with sort of redundant axes where it has the quill and a knee, both can change in Z. So how do we keep track of that, right? And they'll each have their own errors. Let's look at this jig bore machine here and break it down. So if I define these axes, I want to define the table moves in Y, my gantry is X, and my tool moves up and down in Z, right? So what I say is, okay, so my tool is bolted to the Z axis, okay, and then the Z is bolted to X, X is bolted to the frame, Y is bolted to the frame, and my part is on the table, which would be the Y axis. So in sort of notation, I would call this TZXFYP machine, right? So this gives me the chain of components. How do I get the part to align with the tool? I have to go through the Y, through the F, through the X, through the Z, and through the T. Now, this, again, I said that the frame doesn't mean anything unless you want to put a thermal model to the frame or something like that. But if you're just doing dynamic or geometric errors, this frame can drop right out. But again, that's up to you and how complicated you want your model. So again, this 3D printer here, my part is bolted to the Z-axis, and the whole thing actually goes up and down, which is bolted to a Y, and then it's in the frame, and my sort of X-axis is in the frame, and the tool's on the X-axis, right? So it just defines what's bolted to what and in what order. If I move the Z-axis, the only thing that moves is the part, right? But if I move the X-axis, then the tool moves too, right? So that's that. And then when you get into redundant axes, rotary axes, things like that, you have to define some other name, X, Y, Z, ABC. Typically on sort of larger milling machines, this redundant Z-axis would be called W. So for example, on this knee mill I have The tool is in the W axis, which would be the quill, which is in the frame. And then in that chain it comes through the knee mill, or the knee, and then up through the y-axis, up through the x-axis, and then there's the part, right? So this chain of letters really just is a way to keep track of really simply what type of machine do I have, okay? Once you have the machine elements that you want to assign a coordinate system to, right, and typically it's one per axis at the minimum, and then sort of maybe like on that knee mill, the quill is bolted to this thing that can slide, which would be parallel to the X, but it would be fixed, right? So if you wanted to put some little number in your software that, hey, if I change that, I need to remeasure where that position is, and it's really simple. It's just changing one number. So all of these elements don't have to be sort of always changing. They could be static, right? And they could be a future sort of spot in your software, or you could just put it in there, and we'll see that later. But once you have all your machine elements identified, assign a coordinate system to it, right? And then for bookkeeping, assign a name, right? So coordinate system S would be relative to this machine element here. And then you have this order, right? Well, how do I cope with multiple tools on my table? Because that's not really sort of a continuous chain anymore. Now it's more like a tree, right? And if I want to compare that, when I do a G54 offset on a milling machine, what I'm doing is I'm telling my machine that the part coordinate system all of a sudden changed, so that way I can repeat that same code without having to sort of add all of that to that file. So, for example, and in this sort of diagram here, I lay out all of my machine elements, but then you'll notice on this W axis, I've got 3 different elements here. So these would correspond to actually 3 different tools. And in this case, they're all different sensors on a measuring machine. So sort of the equivalent to that would be if you had a touch probe on a 3D printer that would come down and sort of feel the table out, and then it would sort of switch back to the printing head and start printing where you want, or maybe you want to know where your vise is or whatever. It doesn't mean that if I change the milling cutter in a milling machine that I have to switch to a different coordinate system, right? That coordinate system just is going to have a different offset with a different tool offset. So these branches really represent within the same program literally physically different machine elements, okay? And you could do that branch with your tools, like we said with the 3D printer, and you could also do it with the part. So there could be a branch here and a branch here, and then your software can just pick the one chain and the math that gets you to what you need. So the other important step here is to decide, well, what computationally am I going to do the most? So it doesn't actually matter in the math whether I go from the sensor to the part or from the part to the sensor, right? It's actually the same number of operations almost. Okay, so in one you're going to have to transpose or take the inverse of your transformations to go one way or the other, and you have to choose which. So what I like to do just up front is think about, okay, well, if it's a measuring machine, then I'm going to be going from sensor coordinates to part coordinates, because that's how I sort of map out this. We'll say it generates some point cloud in the sensor itself, and then I want to transform that into part coordinates to find out what I'm measuring given all the different configurations of the machine. So in a measuring machine, I would be going from sensor to part very, very frequently, so I don't want to inverse all of my matrices every single time. I just want to pre-multiply them. It's one matrix now, and then I go through with however many points I have that my sensor returns. On the other hand, maybe a single point diamond turning machine, I want to know, how do I get, if I know the tool is at this point on the part, how do I move the machine to get the tool over 1 inch or along a curve or whatever. So all of a sudden now my computation probability or whatever flips the other way. I'm going to be going from part to tool all the time. So again, it doesn't matter which one you choose, it's just an efficiency thing to decide. But whatever you do, you have to pick a direction to do the math. Another thing that you're going to have to do is, after you assign each of these coordinate systems to this machine element, you have to say, where are they in this sort of world that we live in. So this we could talk about in the next video, but this methodology, again, this is sort of where the time savings come in. I won't go through it all right now, but essentially what you do is, again, when the machine's at home, it's gonna do all this stuff, and then it's gonna stop. And then I say, well, where's my tool gonna, or where's my tool gonna be, and then where's my part gonna be, and then I assign coordinate systems that are relative to where that is gonna be most typically, right? So for me, it's 2 inches off the table, right in the center, basically under the tool, right? So I have to go through and very specifically point out and define where I want my first coordinate system. So I'm going to say 2 inches off the plane of the table when all of the axes are in the center of their travel, and then I'm going to say the orientation of that is going to be, if I move X and it's kind of meandering all over, what I'm going to do is I'm going to take the average line of X and I'm going to align my coordinate system, the first coordinate system, to that. That's going to be my x-axis, and then I'm going to say, when I move the Y, it's going to be doing sort of the same thing, but it's going to have, again, some average direction. And then what I do is I say, my Y coordinate system is perpendicular to X, and then the degree of freedom would be along the plane of that XY thing. So even if the Y-axis isn't perpendicular to the X, what it does give you is a sort of rotation about X. Now I have an XY plane, and then I just say Z is perpendicular to those two. And then all other coordinate systems are co-located and co-aligned to that first one. This doesn't make sense obviously for part or the tool, because those change sort of throughout your program possibly, or as you're going from one program to the next. So I say all, but I really mean all but the tool and the part, okay? And by doing this, it saves you a whole lot of headache of physically measuring, well, how far away is my X from my Y, and, you know, is my knee sort of below the quill? It doesn't matter, again. So these coordinate systems don't even actually have to be physically on the machine element themselves. They just have to track with it. If I move the X, then my X axis needs to move along with that. Okay, so it doesn't matter that it's on it, it just needs to be constrained together. And we'll talk about that. But the savings here is, pick a situation that you want to do it at machine home, define your first, and then define all others to that sort of that position, and they're all co-aligned and co-located at machine home, okay? Once you have that, once you have your coordinate systems defined, right, for each element and where they are and what orientation they are from everything else, then you could just go through and then start building your mathematical model. So in this one, remember, for example, this, and back to the letters, would be P, Z, Y, X, F, W, right? And then W has a branch between these three. So if I want to pick the S coordinate system, my equation could be, if I put in part coordinates, I have a transformation matrix to go from P to Z, and then one from Z to Y, one from Y to X, one from here, all the way to, from the last one to the part, or from the coordinate system that I want to be in, right? This kinematic chain gives you that equation, okay? And then this equation is where you have your freedom to put in all of the stuff that you want to track, okay? So for example, this equation here is just for a static machine. It does nothing. That would be that microscope example in the last video. Like, it doesn't actually move and the part doesn't actually move, right? So it's just, if I'm looking through my viewfinder and I want to look at the right side of the viewfinder, what does that mean for the part? And if I want to look at the left, what does that mean for the part, right? So nothing moves, but you can still have different coordinates in one end relative to the other, right? So there's still some freedom even though nothing moves. Well, machine tools move, so how does that work? So what you do then is you just say from part coordinates, I want to transform into the Z coordinate system, but then I want to add my motion from the Z axis, right? And then I transform into Y, add the Y motion, transform, and you just permutate and it gets you back to here. So this gives me a sort of a dynamic model with errors in there. And then also, like I said, when we want to say like, well, I want to track thermal errors, or I want to track dynamic errors. So this transformation matrix will say in this third equation, well, so for example, I transform from part coordinates into the Z coordinate system. I add the Z motion, and then I add sort of a transformation that's a function of how far I move, right? And then this would be like, I need to move plus one more, you know, if I wanted to move 1 inch and I move 0.9999, I need to move that extra, right? So that would be this transformation matrix that's a function of the measured motion, right? And then that propagates all the way through. And you can make this thing as long as you want and have all of these components. And in your software, you could put them in there and have them be the identity matrix, and they do exactly nothing. But they're there for you to later put this in. So don't be afraid to blow this thing up, because computationally it's minimal for a computer. And since you're running this sort of beforehand, or we are, in this example, you don't care really about computational efficiency. It just means that, well, I have to wait an extra 20 seconds before I can transfer my code, right? So if you're doing this at runtime, then maybe this becomes an issue, but really it's how many errors do I actually want to track, really. But the math shouldn't let you decide what you're going to do, right? It's just adding more components into this kinematic chain, which then gives you this equation that you can work from. One thing I'll say is that last slide, that's it. That's the answer. How do I software correct machines? That equation that's it. That is your one sentence answer. The sort of next breath is going to be, well, okay, how do I make that equation? And all it is each of those transformations inside of that list break down into, or could break down into, sort of a recipe how to get from one coordinate system to another. And within each of those, it doesn't really matter what happens in there. It could be completely unique to that sort of, those two elements. But that is a horrible, it's a tremendous, you're going to have to do a lot of effort to kind of keep track of that in your head. So this is where conventions, they're going to, and this sort of forethought is going to save the day in the end, because when something doesn't work, you have to go back in and try and decipher all this, right? And then remember that, well, you have your, it all starts with that equation, but in that equation is a set of functions that give you that matrix in the end. and they kind of look like this. So for example, if I have a 5-axis machine, I have 2 rotational axes. So I have a kinematic chain that tells me, you know, the X is bolted to the Y and then the C is whatever. But what I didn't touch on is, well, there's multiple sort of rotations within one rotational axis, right? So you just need to define a convention on how to step through those. So and this is within each transformation matrix can be compound, right? So, and then this is where your program really starts to break out into a tree. But if you do it this way, it's easy to decompose, because you could say, well, this parameter is wrong. Let me open that one up and find out why. You're not looking at this ginormous string, right? And that's where this notation and matrix sort of notation really comes into play. So again, the order of rotations matters within each of your transformation matrices. And that means that, well, if I have a squareness error and also sort of that is tipped, there's going to be 2 rotational axes inside of this, right? So what that means is I need to, if I want to keep track of these in a way that I can just go back and it's always the same, or I can compare 2 different elements, I want to say that I want to order my rotations in a way that I can just always oh, well, that's what it is, right? So for example, I'm going to transform from coordinate system A to B, okay? Transformation from A to B. I start with A, I rotate around X, right? And then, after it's rotated around X, I rotate around Y, then I rotate around Z, and that gives me coordinate system B. So there should really be one more step in here. For a full transformation, I'm going to do linear translation, and then I'm going to do all my rotations, right? That convention, I'm going to transform linearly and then rotate around X, Y, Z. That always happens every single time. It's in that order every single time, and then that's also how I'm going to measure my errors every single time, okay? But then, if you want to talk even how to get more complicated, so my transformation from A to B, again, I'm going to look at this in my sort of high-level equation, and I'm going to say, well, that represents some vector, and it's an ND vector, but it's some vector from coordinate system A to some coordinate system B, okay? But that really could mean that I'm going to go through this sort of more complicated path. That means that, well, I'm going to put in my geometric offsets and errors first, and then I'm going to say I'm going to essentially add my measured motion, which means that if I multiply in a certain way, it comes out that I add. And then I do dynamic vector or dynamic errors, which again would be like a function of how much I moved. So like that would be like your meandering and things like that. And there could be as many of these as you want. So for example, I would put the thermal model somewhere near the end, right? To say like, well, if my machine has been on this long or I've been working it this much, that gets added in. And then vibration, right? So it's like, well, and if I came to that position with this velocity and with this acceleration, I'm going to add this error in there. And that's how, like in the last video, the Zeiss CMM sort of deals with that wet noodles. This is in there. But again, all of this gets collapsed in your code into one transformation vector, right? So now I can sort of package all of this stuff up and put it in as one number, and if I find that that's wrong, I can start cracking it open. And then even within these, my geometric offsets and errors is going to have linear and rotational components. So, you know, it's like if you thought about writing this out or like putting this all in one equation, that's crazy. Let this notation be your guide to sort of package these components into digestible chunks that you could easily evaluate. Okay, and then there's this concept of, remember when I said you have to pick a direction? Am I going from A to B, or am I going from B to A, right? So mathematically, it doesn't matter if whether I go from A to B or B to A. If I physically measure this from A to B, it's going to be plus, plus, so plus X plus Y. But if I put this into a matrix form, because this is a coordinate system transformation and not a coordinate transformation, I'm not moving my point of interest, I'm moving my reference. Remember, so I'm not moving the part to the tool, I'm moving the tool to the part. Mathematically it doesn't matter, but from a bookkeeping standpoint and math, in sort of sanity, it matters a great deal. So if you go from A to B and I physically measure from A to B, then my transformation matrix is going to have a lot of negatives in it. And that's fine as long as there's always those negatives. So what I like to do is go from my math is in the opposite direction of what I'm physically measuring, and then these negatives drop out. But I have to remember that this is the measured X from A to B, even though this is the transformation from B to A. Okay, so whatever you want to do, just always do it that way. Pick a convention, okay? And then, so if I was to say I want to go from A to C, I have to go through this B, so I translate to B and then rotate into C, okay? So the transformation matrix in 2D from B to C, just a simple rotation, which one is it? Okay? Technically, every single one of these is right. Okay, they'll get you, mathematically, they're all correct to get you from here to here. But one is from C to B, one is from B to C, and then do I take the negative out and put it into my transformation matrix, right? Both of these are correct. So cosine is a symmetric function, the negative goes away, but the sine is not. So here I have a negative outside the sine, it's double negative, which makes this positive, and then this negative drops out. So this is mirrored, right? So what it ends up being is if you Google rotation matrix, rotation about Z for a 2D system, this is the equation you're going to get. The minus sign is going to be on this top right component. But, well, wait a minute, we're going backwards because we're not moving the point, we're moving the reference. So this equation is actually the real equation. But again, when you're troubleshooting, I want to know that if I Google this really quick, I want to see this equation, that's what I want to see in my code. Okay, but to get rid of this minus sign, I go from C to B, but I measure from B to C. Okay, so you're measuring opposite of the kinematic chain, and it sort of condenses the math a little bit better, but you sort of lose these minus signs. Because remember, for a machine that's more right than wrong, these errors are going to be very small. So is it minus plus 1 degree or plus 0.1 degree? Like, you can't see that. So you can't even know the sign. So you have to be very, very, very diligent about keeping track of conventions and bookkeeping, and then you can try it, and if it's, if it's wrong, then it's only a matter of changing a sign within the measured thing and never switching the equations, okay? So again, conventions, conventions, conventions. Whatever you do it every time. So in software world, that lends itself to building a function. That way, oh, my convention changed halfway through the program. It happens, it's okay. But I want to change it once, not for every single machine element. So functions are your friend. Build the conventions into the functions and break it down from my one transformation matrix is actually a function of many, which is actually a function. Each of those is actually a function of many. Okay, so break it down. Otherwise, it's going to get so complicated you're going to give up. Just keep with convention, let functions be your friend, and this math will take care of itself. So everything that we've talked about up to now mathematically has been forward transformations. That means that if I know everything that's within all of my transformation matrices, I can go from one coordinate system to another, right? In this case, part to the tool. Well, that doesn't help me with saying if I know these, how do I get there? How do I position my machine? And there's no quick answer for how to solve inverse kinematics. Okay, this is sort of a game of logic. There's analytic solutions, there's numeric solutions, but let's talk about these. But that, just beware, there's no quick answer for how do I get my machine to do here, and this is why. So if I, again, just to sort of backtrack just a little bit, in this equation I have a part coordinate. Okay, I'm going to transform linearly from P to X, and that represents my geometric errors and offsets relative to that transformation, okay? And then I'm going to transform linearly, and it's going to be my XM means measured motion, okay? So again, this is where naming conventions really help with this bookkeeping to keep your kinematic chain sort of recognizable even in its short form, okay? So geometric, measure, geometric, measure, geometric. So what I have here is a 2-axis machine with errors or offsets in between each machine element. So I've got 2 axes and 2 apart in a tool. So I have 5 transformation matrices, right? So let's look at this in its expanded form, right? So I have, let's just say I'm at 0, 0 in the part, and I have my measured motion here and here, and each of these is the identity matrix, so it does nothing. So essentially, XM drops through, and so does YM, right? So in this instance, it's quicker to just think, hey, well, my overall transformation is I add, these just propagate straight through, right? So it's simple. Now if I throw a rotation in there, so in this equation my offset between the part offset and my tool offset drop out, and I just, for the sake of simplicity, I just put in here XM, YM, and then some rotation angle. Well, now all of a sudden my forward equation comes from, well, now my tool coordinate is no longer just, these don't go straight through. Now my tool, my X coordinate in my tool coordinate system is a function of my measured motion of both Y and X. Okay, so, and that follows through here. So now all of a sudden my sort of really easy analytic solution gets really complicated because now it's a system of equations. But there still is an analytic solution for this because there's no redundant x's. There's only one solution that will make this true. Okay, there's only one set of numbers for here and here that will make this whole equation true. And then that basically looks like this. If I know my tool coordinate and I know my part coordinate, what do I have to do to solve this equation? And that means how do I have to move my X and my Y to align these two pieces, these two points in space with a certain orientation, mind you. Okay, like I just said, the analytic solution is not always the best because you have to solve a system of equations, and if you have a solver, great. You know, there's definitely software packages that can do that for you. If you're like I was, a couple of years ago, then well, I just want to do it quickly. So an analytic solution is going to give me a quicker result than me finding a package and paying for it or figuring it out or whatever. I just read a quick solve block to do this. And for simple machines, this is the methodology that I would do. So what we're looking at here is I'm looking at sort of a drawing of that same 2-axis machine, but now I have a rotation error between X and Y. Okay, so my X axis represents the direction that I can move the part or the tool in along the X, and then the Y axis is where my Y axis is going to move. Okay, so this angle means that if I want to get to this point, I can't just drive over and then up, it'll be wrong. But that's okay. So what I do is I simulate the move, right? Because I can guess a number and then recalculate and then find out where I am, basically what my error is, right? So I'm going to simulate my move, but what I'm going to do is I'm just going to take the X and Y coordinate of that part and then I'm just going to punch it right in. And then like I said, oh, I'm here, not here, right? So then I just say, now that's my new starting point, and I simulate another move to here, and then I add the new X, sort of the new required move to the old one, and then that gets me closer. Okay, so then what I do is I just put this into a solve block and say, when my error is smaller than I care about, stop. Okay, and then that gives me the actual vector that I need to move to get to where I need to be in one shot. So my machine's not physically spiraling around to that point. It's actually, again, when we run the code before, we solve all these stuff, and then when I type in my linear, when it returns the coordinate in the G-code interpreter, it'll just go from one point to the next. Okay, so this is the fundamental thing about solving for simple machines. This is what I do every time. It's fast, it's so fast. A computer can do this within seconds. And like I said, if your machine is more right than wrong, you're not talking thousands of iterations, you're talking like 3, right? So even in this crazy diagram here where it's like a 15-degree error or something like that, the second one gets me really, really close, right? So again, you're talking maybe 10 iterations per point, and I don't know, maybe there's a million lines of G-code or whatever, but it's not crazy, right? For a computer, it'll blow through that so fast, even a laptop. So when I say there's no single analytic solution that can solve that, the reason is because, for example, on this 5-axis machine, every single one of these points, the tool is aligned with my part. So it's a little bit more complicated than that all of a sudden. Well, I got to track my orientation as well. So for these types of situations where it's more complicated like that, what I do is break it into components, and we'll go into sort of an arm in a second. But for example, for this 5-axis machine, well, every single one of these solutions gets my tool to the part where I want it, but the rotation's wrong. So what that means mathematically is the angular solution is singular, like there's only one angle that I want to be at, but then my position solution is non-singular. Yeah, there's many positions that's going to align this depending on my orientation. So you can see that the gantry has to move to bring this over, right? So well, what I do then is break that into 2 steps. So first I solve my angular component. So it's like, what does it take to get this machine into the angle that I want? It could be like way over here, that's fine. Solve the angular component, and then what do I got to do to get my tool to where it needs to be now? Okay, so all of a sudden it turns back into that quick solve block, but it's a 2-step problem. So you have to think about this for your own machine. That's why I say there's no exact solution for that machine. Now there are software packages that'll do all this for you, but this is basically what they're doing, right? You type in a tolerance and it just solves the thing either numerically or analytically, right? So it's, and again, it's just an efficiency issue. Can you imagine? Can you imagine this? Okay. Like if I walked in there, I'd be like, this is gonna take me 5 years, right? And the reason is because even though you solve that equation, well, your shoulder might be driving through the car, or your elbow, your wrist might be some weird direction. So any solution is not necessarily the best solution, right? So if it's non-singular, then you have to all of a sudden start making decisions on what. Oh, right? So you just break it down into say, well, I've only got, on this robot, I've only got one waist. Okay, so that means that wherever my arm needs to be, like obviously I need to move that first. Okay, even though my wrist has sort of a component that's along the waist, right? I can have a preferred axis, and then I want to sort of move that first, and then I want to figure out what I need to do the rest. So there's a couple things that you need to think about while you're going through that methodology of how I do this. So, and just to be very clear, like they don't do this mathematically, no. What they do is you use this remote, drive my arm to where it needs to be, I put the windshield in the hole, and then I say, well, now mathematically I just want to go from here to here, okay? Or if this is a welding robot, I want to go from here in a straight line to here. So again, break it down, like solve your pose first and then do the math, okay? And a lot of times on smaller robots, you just like grab the arm, put it into kinematic teaching mode, and you grab the arm and you just move it around and it remembers this sort of stuff. But, so solutions aside, any solution is not the best solution. So you have to remember your environmental constraints. Where are my clamps? Where's the machine axes in space? Is this thing gonna like try and mill through the vise to machine a sphere, right? So again, you just need to be thinking about all this, and it's much more complicated on a 5-axis machine than it is a 3D printer, right? There's not much you can do to a 3D printer, but if it's a rotational axis, obviously you can't drive through it, right? So consider your environment. Then, for example, rotary axes wrap. It goes from 0 to 360, but then it keeps going. Back to 361 is the same as 1, right? So when I solve for this, I might be at 359 and I need to go to 2. Well, my solution might tell me, well, I need to reverse back down to 2. Well, that's horrible. So look for wrapping opportunities and things like that, and then also consider your axis limits. I can't solve that because my axis can't actually go that far, right? And maybe you can leave that up to your machine, but at runtime, but what if there was another solution that could be solved within the limits of your machine? So you got to think about that. And then efficiency, I just said that. On the knee mill, in the previous example, or like really big CNC centers, there's only, so in your precision axes, there's only so much motion that you want to do. Like the longer the axis, the less precision you're going to have. So what they do is they say, well, if I'm milling like a big tall part, I want to move my precision axis up. I want to physically move that whole thing. So just like on a Bridgeport, you can unbolt the thing and slide the head in and out. That's not like a controllable axis, but it's still an element that you can change. So on these big CNC machines, say if it looks like a Bridgeport with the table on the bottom and a Z-axis sort of hanging off the frame, well, this thing like unlocks the brakes and like moves the whole head up and down and then relocks. But that's not something that you're going to do while you're machining. It's just there to kind of give you a little bit more flexibility in the parts you are machining. So in that solution, obviously it's like, if I can get there without moving the big one, do it. Otherwise, maybe ask the user, hey, is this even right? Like, should I do this? Or maybe it's doing it to do a tool change or something like that. So that's the preferred axis sort of stuff. You got to think about which one do I move first. But if you don't have redundant axes, you don't have to worry about it. Anyways, that's it. In a nutshell, that's how to software correct a machine. And then, so in the next video, we'll actually go through the one that I did in the demo, and we'll actually go through and talk about how I measured the errors and things like that. I also want to talk about maybe what's available out there to sort of measure errors in certain situations. There's a whole nother topic on how to do that efficiently and with zero uncertainty, things like reversal techniques. So if you have a bent straight edge, for example, well, if I flip the straight edge around and measure it again, well, now my errors are exactly opposite of the way I measured it before. So then they negate into a perfect straight edge, right? So all of a sudden now my $5,000 zero door tiny little gauge block that's almost perfect just turned perfect. Or maybe my $20 CNC vice jaw, right, all of a sudden has much more precision than I can even cut it. So there's some things that we could do. I might touch into that, but I'll certainly walk through how I'm setting up my coordinate systems, how I'm measuring them, and in this example, I'll do it all with tools that you could get from even Harbor Freight, right? So it all depends on what sort of level of accuracy you're trying to achieve. So obviously you're not going to correct a diamond turning machine with this dial gauge, right? You're just not going to do it. But in this example, it doesn't mean anything to me because the machine doesn't do anything, but this dial gauge, reading to a 10,000th or something is much more accurate than any part that you're going to need to make for any kind of like steam engine or car part or anything that the hobbyists would ever want to make. Like these 1/10,000th of an inch is, think about a piston or a bearing, a journal bearing in a car, like the tolerance is 1 or 2 thousandths. So don't get hung up on it. But for like the 3D printing people, you want to, on a machine that's made out of rubber and plastic, like you want to calibrate that every single time you turn it on, and this is more than enough, right? So you can even build a one button auto calibration that'll just bzzz, it'll do all that, in like a minute or 2 minutes or 5 minutes or whatever. But yeah, so you don't need crazy expensive tools, and with reversal techniques and things we can minimize some of that error. But keep in mind that a lot of that stuff really does exist, and there's lasers that you bolt to the table and align to one axis, and it'll measure all 6 degrees of freedom as you're going through each of your moves, right? So hundreds of thousands of dollars for that equipment and to have that done, but maybe this might be enough for you. So see you next time. Thank you.